will be 2 times of complex multiplication, which means that uh, one complex multiplication contains two real additions. So the number of real additions involved in the complex multiplication operations will be 2 times of the complex multiplication operations. Similarly, real additions will be 2 times of the complex addition operation, because every complex addition contains two real additions. Now we are doing this working for a single row, so we have to write the formulas of complex multiplication and complex addition for a single row, which we have discussed in earlier slides. So for a single row, number of complex multiplications are n, and for a single row the number of complex additions are n minus 1, and after multiplying n and n minus 1 with 2, it will become 2n plus 2n minus 2, or simply 4n minus 2. So these are the real additions for a single row. And for the whole matrix, or for n number of rows, we can multiply 4n minus 2 with n, which will make it 4n square minus 2n real additions. So whenever we will perform n-point DFT, 4n square minus 2n real additions will be performed. And the total number of real computations will be the summation of real multiplications and real additions. So real multiplications are 4n square, while the number of real additions are 4n square minus 2n. And finally we will get 8n square minus 2n real computations. So in n-point DFT, our computer has to perform 8n square minus 2n real computations. Now, the order of computations, or the computational complexity, or the computational cost of the standard DFT equation is n square. This n square factor is basically the common factor in all those four formulas which we have just discussed. The formula of complex multiplication was n square, the formula of complex addition was n square minus n, the formula of real multiplications was 4n square, the formula of real additions was 4n square minus 2n. So in all those four formulas, n square is basically the common factor, which is basically the order of computations in standard DFT. Now let's discuss how good or bad is this order of computation. Basically, n square is considered as a very higher order of computation in the field of programming, because it shows that when we'll increase the value of n linearly, where n represents the length of DFT, then the requirement of computations performed by our computer will increase non-linearly. Or more specifically, we can say that the requirement of computations will be increased in a squared order. So if we are going to take a very higher point DFT, or if the value of n is very large, then it will need a lot of computations. And this squared order of computations is the main reason which makes DFT computationally very slow, or an inefficient technique. Now let's discuss some numerical examples. In the first example, we have to find number of complex and real computations for 1024 point DFT. So here capital N is equal to 1024, and we can use these two formulas of complex and real computations. So the number of complex computations are 2n square minus n, while the formula of real computations is 8n square minus 2n. So just put the value of n is equal to 1024 and get these results. Now the conclusion is, for calculating 1024 point DFT, our computer needs to perform 2.096 million complex computations. Or in other words, our computer needs to perform 8.386 million real computations in order to provide the result of 1024 point DFT. So you can simply imagine that you are taking samples of a time domain signal, and you are providing 1024 points or 1024 samples of a time domain sequence to your computer, and your computer is processing those 1024 samples with the help of 8.386 million computations in order to return back the 1024 points or 1024 samples in the frequency domain. So this is the main drawback of this n square factor in the formulas of computations of standard DFT, because as you can see, the number of samples were in just the thousandth order, while the requirement of computations is in a millionth order. Now let's come to the second numerical, which is a very interesting example. It says that the sampling rate is 512 samples per second and the length of DFT operation is also 512 samples. So this is Fs and this is capital N. Now if the processor can solve one real computation in one clock cycle, then calculate the minimum processor speed that can perform DFT operation in real time. Now, before solving this numerical, we will first discuss very briefly what is the meaning of clock cycle. Basically, the speed of a computer processor is determined in terms of clock cycles. So, this is a series of clock pulses which is continuously going on, and how many clock pulses our computer will have, it will depend on the processor speed. So, if the processor speed is 1 megahertz, then it means it will have 1 million clock pulses in the 1 second duration. And if the processor speed is 1 gigahertz, then it will have 1 billion such clock pulses over the 1 second duration. So depending upon the frequency or the speed of a processor, we can simply determine the time duration of one cycle, which will be simply the inverse of the processor speed, which means that for a 1 megahertz processor, the time of one cycle will be equal to 1 microsecond. Similarly, for the 1 gigahertz processor, the time interval of the one cycle will be equal to 1 nanosecond. So what is the definition of one clock cycle? It is just the time interval between two adjacent clock pulses of an oscillator. And generally speaking, the higher the number of clock pulses in a 1 second duration, the faster will be the processor ability to handle the information. So this is the idea of one clock cycle interval. And our computers execute different instructions in terms of clock cycle duration, because it shows that how much time will be needed by our computer to perform the desired task. It is usually defined in terms of number of clock cycles. Like in our case, it is defined that our computer can solve one real computation in one clock cycle duration. So it means that during a one cycle duration, our computer can solve one real computation. And early computers or slower processors were designed to perform one computation in one clock cycle, but the modern processor and the faster processors can even execute multiple instructions during the one clock cycle interval. Now let's come to the solution of the given numerical. With the help of given data, we can find processor speed by multiplying three quantities, where the first quantity is computations per DFT, the second quantity is DFT operations per second, while the third quantity is cycles per computation. And you can also check their units. On the simplification of the units of these three quantities, finally we will get number of cycles per second, which is also called the hertz. So the first quantity which is required to calculate for the calculation of processor speed is number of computations per DFT operation, which shows that how many computations will be required for a single DFT operation. While the second quantity is number of DFT operations per second, which shows that how many times we will calculate DFT in a single second. While the third quantity is about the processor architecture, which shows that number of cycles required to solve a single computation. Please remember that it is cycles per computation, not the computations per cycle. And you can remember this thing by remembering the final unit, which we want to obtain, it should be in cycles per second. So we must have to keep cycles in the numerator. So the third quantity is cycles per computation, not the computations per cycle. Now let's calculate the first quantity, which is number of real computations per DFT operation, and the formula of real computations is 8n square minus 2n, and the value of n which was given to us in the numerical statement, it was equal to 512 samples. So just put n is equal to 512 here, and after solving it we will get the final result equal to this value. So it shows that for applying DFT on 512 samples, our processor needs to perform 2.096 million computations for a single DFT operation. Now let's come to the second quantity, which is about total number of DFT operations performed in 1 second. As we discussed the numerical statement, the sampling speed of ADC was 512 samples per second, and the length of DFT was also 512 samples. So in the second quantity, we have to find how many times computer can perform DFT operation in 1 second. So just think about it. If the ADC sampling speed is 512 samples per second and the length of DFT is also 512 samples, then how many times we can apply DFT on a given sequence? So the answer is we can perform DFT only once, because every DFT operation is waiting for 512 samples, and our ADC is providing the required number of samples in 1 second. So definitely we can perform only one DFT operation in a single second. So basically this quantity depends on two quantities, what is the value of fs and what is the value of n. So it can be calculated by taking a ratio of fs and n. And if you will check the units of these two quantities, the unit of fs is samples per second, and the unit of n is usually expressed as samples, but more specifically in this case we can write the unit of n as number of samples per DFT operation, because DFT is applied on n number of samples. So after simplifying the units, the final unit will be DFT per second. So this was the second quantity which was required to calculate for the processor speed calculation. Now the third quantity is very simple. In the numerical statement it was given that our computer can solve one computation in one cycle. So the total cycles per computation is simply equal to 1. So after getting these three quantities we can simply multiply them. Now on multiplying all three quantities which were calculated individually, we will get the final result of processor speed equal to 2.096128 megahertz, which means that we must have to use 2.096 megahertz processor in order to meet the required specifications. And the conclusion of this numerical is that if we will use the 2.096 megahertz computer, then it will have 2.096 million clock pulses in 1 second. And as the processor architecture which was given in the numerical statement, it can solve one computation in one clock cycle duration. And the requirement of computations were also 2.096 million computations. So it means that the resultant processor will solve every real computation in a single clock cycle duration. So after completing 2.096 million number of clock cycles, all the computations will be done by our processor, and after those required computations we will get the results of Fourier transform. Now let's discuss the third numerical